Welcome back, everybody. So we're in our last week of the course and realize the final exam is already passed and we've completed that. We have a couple of topics to finish up. These are topics that are a little more difficult, so I didn't feel fair putting them on the final exam, but they're ones that could be handy going forward. So we're actually jumping back to chapter 5 where we talked about discrete probability distributions. And we had talked about just regular discrete distributions, and then we talked about the binomial probability distribution in chapter 5. We want to add in another one that actually gets used quite often in practical application, and that's the Poisson distribution. Now, there are a couple others in there. There's called the geometric distribution. A geometric distribution is similar to a binomial distribution, but instead of saying what's the probability that a certain number of occurrences will happen out of so many trials, it is actually calculating the probability that the first occurrence will happen on a certain trial. So how many trials does it take to get to the first occurrence is what the geometric distribution talks about. And then the hypergeometric distribution that is related also to the binomial distribution in that it's basically the binomial distribution but without replacement. So like drawing cards from a deck of cards where you want to draw a hand of 5 cards, you're not going to put them back. You're not going to put the first card back before you draw the second one. So you're drawing out without replacement, and the hypergeometric distribution fits those probabilities. If you were to go on to a more advanced statistics course, you would expect to see those two distributions talked about extensively as well. We'll maybe come back at the end of this little presentation here, and we'll do an example of each of the geometric distribution and the hypergeometric. But really, all we're concentrating on for this course is the Poisson distribution. So we're going to look at calculating probabilities from the Poisson distribution here, which is another discrete probability distribution. And so the Poisson distribution measures is the number of occurrences of an event that would occur over a specific interval. Typically, that interval is going to be an interval of time, but it could be a length, an area, could even be a run of parts, a number of parts contained, produced, I should say. The formula for the Poisson probability, the probability of having X occurrences over an interval, is mu. And I remember mu is going to be the mean number of occurrences over that interval to the power of X times E, where E is a natural constant. It is E equals 2.71828 to the power of negative mu, and then over X factorial. Now remember, X factorial, if it's 4 factorial, that's 4 times 3 times 2 times 1. X factorial, whatever value X is, it's going to be that factorial multiplied out. You might be looking at this value of E saying, well, how am I going to remember that? You don't have to. I will show you where there's a button on the calculator that does that for you. So again, requirements for the Poisson distribution is we're looking at random events occurring over an interval. How many events occur over that interval? And the occurrence of those events must be random. The occurrence of one event must be independent from the others. And it must be, now when they say uniformly distributed, that's kind of deceiving. It makes you think like they're evenly spaced over the interval. That is not true. They're not necessarily evenly spaced, but what uniformly distributed means is at each point in time along that interval, or each point along that interval, there's an equal chance of that event occurring. So it's not like it's more likely to occur towards the beginning or the end of the interval, or nothing going on that would make it more likely to happen at different spots in that interval. So the parameters. So mu is the mean. The standard deviation then can be found in this. This is the only distribution that has this quality. The standard deviation is just the square root of that mean, the square root of mu. So the properties of the distribution, a particular Poisson distribution, is determined only by its mean. So that's the only parameter that matters in calculating with this distribution. And the values start at 0. There could be 0 occurrences on that interval up to an infinite number. There's no upper limit. Think of potholes in a road. If on average there's 4 potholes in a mile, if you randomly select a mile of road somewhere, there could be 0 potholes in it, or there could be as many potholes as you can imagine. So the example we're going to look at here, we're going to look at Atlantic hurricanes. So there have been 652 Atlantic hurricanes during the past 118-year period. That's starting in 1900, going up to 2018. So obviously this data is a few years old. We're going to assume that the Poisson distribution is suitable. We're going to calculate the probabilities. Then we're going to come back and analyze that to see if the Poisson distribution seemed to be appropriate, see if it seemed to fit. So the first thing we want to do is we're going to want to find the mean number of hurricanes per year. We'll do that on the next slide. Then we're going to calculate the probability of getting 6 hurricanes in 1 year. Then we're going to compare that to what actually occurred, and we're going to see if the Poisson distribution seems like a reasonable approximation for that. So here, find the number of hurricanes per year, the average number of hurricanes per year. Well, we take 652 hurricanes divided by 118 years, gives us 5.5 hurricanes per year is the mean. So that is mu. To find the probability of 6 hurricanes, so we put X, 6 goes in for X, mu is 5.5, E is that 2.71. Now I'm going to build up the calculator here. So I'm going to show you how to enter this in a calculator. Most of your calculators have the power key. It would be this caret key like that. So that's what we're going to give you to the power of. So we're going to start out with mu of 5.5 to the power of 6, then times. Now where to get the E? You can see here above the ln key, there's e to the x. So do second, e to the x. That's e to the power of. That's exactly what we want. Now you have to remember, put in the negative here. It's negative mu there. So negative 5.5. We're going to close the parentheses on that. Then we have to divide by x factorial. So x is 6. To put in the factorial, we go to math, probability, and option number 4 there is our factorial. If I hit enter, I get 0.1571, exactly what we got here on our slide for our probability. So the probability of getting exactly 6 hurricanes in a year is 0.157. Now analyze if this is a good approximation according to history. So data tells us that in that 118-year period, there were exactly 16 years where they had 6 hurricanes during that year. Well, if we go back to that 118 years times our probability we found of 0.157, that would give us an expected value of 18.5 years. Now, 18.5 years and 16 years are pretty darn close. We're only off by 2.5 there. So getting an observed value of 16 and a calculated value there of 18.5 years is pretty darn close. So that's telling us that the Poisson model was actually a pretty good model for this. And so I'm sure you can see with this how the Poisson model can be pretty powerful. If we know the history of something, we can predict how often it's going to happen in the future. The Poisson model also can be used, the Poisson distribution, I should say, can also be used to approximate binomial probabilities. Seems like we're always trying to approximate binomial probabilities. Binomial probabilities, they had that huge long formula, if you remember, where we had combinations and factorials and powers and all that. It's a large formula. And the probability tables for each value of n, for each number of trials, you have to have a different table. So literally they had books and books full of probability tables for binomial distribution. Well, if you wanted a large number, you're going to use you're going to either have to add up a lot of numbers together to get to that. That's why we use the normal approximation that we saw back in week 5. So the normal approximation took care of that. If you had a large number of possibilities you had to add up, it give you that cumulative effect. The Poisson approximation is used if we have a large number of trials, like more than 100. So most of your tables, they didn't go over n equals 100, so we had to do something else to approximate that calculation. So if we have more than 100 trials, we also need that requirement, n times p must be at least 10. We must expect at least 10 successes in that interval. The Poisson distribution does a good job of estimating binomial calculations without having to go through the big long formula and without having to get extra tables for probability tables. So here, both requirements are satisfied if we want to. So if both requirements are satisfied, we want to use the Poisson distribution as approximation for this binomial distribution, simply because it's an easier calculation. It's just a formula. So in the main pick 4 game, you pay 50 cents and you get to select a 4-digit number. So 4 digits, each digit has to be 0 through 9. So an example would be 1377 is one possible play. If you did this every day for a year, what is the probability that you would win at least once during the year? So now remember, at least once, probability that x is greater than or equal to 1. That's at least once. Now that would mean we'd have to find the probability that x equals 1, probability that x equals 2, all the way up to x equals 365. We don't want to calculate 365 probabilities and add them together. So we're going to use the complement. The complement of winning at least once is winning 0 times. The probability that x equals 0. And remember, the relationship between the complements is the probability that x is greater than or equal to 1 is equal to 1 minus the probability of its complement. So we just find the probability of x equals 0. We'll subtract it from 1 to get the probability of winning at least once. So again, here's our game. There are 4 digits and 10 possibilities. So 10 to the power of 4 is 10,000 possibilities. So 1 over 10,000 gives us a 0.0001 probability of winning on a given day, or 1 in 10,000. So then our mean number of occurrences, or expected number of occurrences here, is 365 days times that 1 over 10,000, or the 0.0001, giving us that we expect to have 0.0365 occurrences per year. So then we bring that back and we're going to plug it into the Poisson distribution formula here. Again, I'm going to punch this in the calculator along with you. So we start with that mean expected value of 0.0365 to the power of 0. Remember, we're finding the probability of not winning at all, because that's the complement of winning at least once, times, and I'm going to do second e to the x, negative 0.0365. We're going to close that parentheses. And we're going to divide by 0 factorial. So I'm just going 0, math, probability, factorial. 0 factorial is 1, by the way, as you can see in the slide. Mu to the power of 0, anything to the power of 0 is also 1. So this really all reduces down to this e to the power of negative 0.0365, which is going to give us 0.9642, they're rounding it to, so 0.9642. Now remember, that's the probability of not winning, which sounds reasonable. It's a pretty high probability, and it's a pretty good chance you're not going to win. So it's the probability that you will win. It's the complement. We take 1 minus the probability of not winning. So it's a 0.0358 chance that you'll win at least once. So basically, 3.5% chance that you'll win at least once during the year. So let's do some other examples here of the Poisson distribution. Actually, I want to show you in Excel, there is an Excel function for the Poisson distribution. If I wanted to do equals Poisson, so what we're looking at here, we wanted 0 occurrences, the mean of 0.0365, cumulative, we're just going to put 1 in there for true. And we get, there's the number we had, and of course, equals 1 minus that, gave us that 0.0358, so that 3.5% that we calculated before. Well, since we're here, let's do the binomial calculation. So the binomial distribution here, number of successes, 0 out of 365 trials. The probability was 10,000, and yes, cumulative. Oops, keep forgetting you can't put yes in there. You either got to put in true or 1. And there I get the same probability almost. It's the 6th decimal place that it's actually different. So if I did equals 1 minus that, virtually identical probability. Now, as the number of trials gets smaller, if we had less than 100 trials, if I just wanted to say what's the probability of winning at least once during a month, that trials being smaller, there's going to be a bigger difference between the binomial and the Poisson approximation. So it's important that we only use the Poisson approximation of the binomial distribution if we have a large number of trials. That at least n equals 100 is a good ground rule for that. So now let's take a look at some other examples here of binomial or the Poisson distribution. So let's say here we're going to have, on average, we brought up potholes. Let's talk about potholes. On average, every mile of fiber optic, actually we're talking about potholes, talking about fiber optic here. Every mile of fiber optic cable has 6 nodes. A node is simply where they tap into the cable to pull off a signal to go to a household. What is the probability that a 9-mile stretch of fiber optic cable will have exactly 50 nodes? So first, we want to find the mean. Or I always like to put it as the expected value. Remember, the mean is expected value is another way of saying the mean. So to do this, we have 9 miles times an average of 6 nodes per mile. That gives us 54 nodes is the expected value. That's our mu. So to find our probability, that x equals 50 is going to equal mu 54 to the power of 50 times e to the power of negative 54, negative mu, over 50 factorial. So this is a little bit bigger calculation, but the calculator handles this just fine. So it's 54 to the power of 50 times second e to the x, negative 54, close, divided by 50 factorial. So 50, we go to math, probability, option 4 is factorial. We hit equals and we get 0.0484. So just under 5% is the chance that there will be 50 nodes on that 9-mile stretch. I had mentioned a couple other distributions, so let's take a look at those. Let's look at geometric distribution here. Now, at this point, this is strictly for your information. This will not be in the homework for week 16. But a geometric distribution is the probability that you'll get the first success on a given trial. So it has all the requirements of the binomial distribution except for having a set number of trials. The trials are still independent. So the result of one trial does not affect the result of the next. Every trial is either a success or a failure. And P, which is the probability of success, is constant from one to the next. So the probability of success does not change from one trial to the next. So the probability that the first success is on trial X is found by using the formula. The probability of X is equal to 1 minus P to the power of X minus 1 times P. So if you think back to the binomial distribution, X minus 1 is the number of trials before we get to that X trial. 1 minus P is the probability of failure. We need that many failures to occur and then get the success. There's no combinations here because there is no variation in order. The success has to be the last one. So an example here, if we say that 45% of students carry a laptop to class, if we randomly stop students and check for a laptop, obviously not stopping them and searching them, we're just stopping them and asking them if they have a laptop with them. What is the probability that the fourth student will be the first one with a laptop? So P, probability of having a laptop, is 0.45. That's from the 45% here. X is 4. We're asking the fourth student to be our success. So the probability here of 4 is equal to 1 minus 0.45 to the power of 4 minus 1, which is 3, of course, times P of 0.45. So on the calculator, parentheses 1 minus, oops, not that key, 1 minus 0.45, parentheses to the power of 4 minus 1, close parentheses, times 0.45. We get 0.0749. So about a 7.5% chance that the fourth person will be the first student to have a computer on them. So that's how the geometric distribution works. Let's talk a little bit about the hypergeometric distribution. Again, hypergeometric distribution is not in this course. You're not going to be tested on it. So the formula here is it's combinations. So it's going to be the probability of X in Y. Of having X successes in a sample. So X is the number of successes in a sample. Y is the number of successes in the population. So obviously this is looking at a finite population, a limited population, countable population. N is the size of the sample. M is going to be the size of the population. So if I have a 4C2, what that is saying is 4 factorial over 4 minus 2 factorial times 2 factorial. That's what that notation means. So the probability that we have exactly X successes in our sample is equal to X combination Y times M. Got back up just a second here. I wrote this down wrong. This should be Y choose X. M minus Y choose N minus X divided by M choose N. Now there's a lot of notation here. So let's get straight to an example, and then we'll put the numbers in this. So our example is if we have marbles in a box, 6 red and 4 blue marbles in a box. And I want to know what is the probability if we select 3 marbles without replacement. So remember, without replacement means we pick one marble out, we record whether it's red or blue, and then we set it aside. We do not put it back in the box. If we put it back in the box, if we did the with replacement, then this is a binomial probability. So if we select 3 marbles without replacement, what is the probability of exactly 2 being red? So N equals 3 because we're choosing 3 marbles. X equals 2 because we want 2 of them to be red. M equals 10 because there's 10 total marbles in the box. 6 plus 4 is 10. And Y equals 6 because there are 6 red marbles total. So this is going to be 6 choose 2 times 10 minus 6 choose 3 minus 2 over 10 choose 3. So how do I enter this in the calculator? Well, we're going to use that math function, that math menu. So 6 math, probability, option 3, NCR, 2 times, oops, yeah, this should work. 10 minus 6, I'm just going to enter the 4 there. Math, NCR, 3 minus 2 is 1. Divided by 10, math, NCR, 3. Gives us a 0.5. So it's actually a 0.5 probability that we end up getting 2 of the 3 marbles being red. So again, that's just another example of our probability distributions. For this course, we're only going to be responsible for that Poisson distribution that we saw up above. Make sure you're good with that. There will be homework on it in my math lab. There is a quiz, but this will not be on any of our unit tests or any of that. So with that, I will close this video down and we'll come back to talk about ANOVA testing.